Good afternoon. Thank you for the honor of presenting here. So, my name's Sonia Voiculescu. I'll be talking about this window into metastasis, and it's actually something we developed with a partnership between Montefiore Department of Surgery and Albert Einstein College of Medicine on a T32 grant. So I have nothing to disclose, so my work was done in the Candelas lab, and for many years the Candelas lab has studied the tumor microenvironment of metastasis, and they've used a very interesting tool, which is multiphoton microscopy. So here's an example. This is a 3D reconstruction of a tumor cell and a macrophage moving together and docking on this blood vessel here. And they've studied this for years and years, and they actually came up with a term called tumor microenvironment of metastasis of this tripartite structure. And the structure actually, when it's active, causes vascular permeability, as you can see here. And using subcellular resolution and getting even closer to what's going on, we were able to realize that it's not just the site of vascular permeability or leakiness, it's also where tumor cells inject into the bloodstream and the site of hematogenous dissemination. So in short, this little cartoon kind of shows you what happens in the metastatic process. The tumor cells break free from the primary tumor, they stream through the stroma, they pair up with these specific tumor-associated macrophages and arrive onto the blood vessel, and they create the TMEM, the tumor microenvironment of metastasis. And we found this structure in secondary sites, in metastatic sites, both in mice that we study and in patients, unfortunately, that have succumbed to metastatic breast cancer. So this begs the question, does TMEM function everywhere in the same way? Does it use the same mechanism and function the same way? So throughout the years, people have tried to study the lung in vivo. This is one of the most common sites of distant metastasis. And as you can see here, just recently the technology has been miniaturized to be used in mice, and with the latest work employing vacuum stabilization. However, this only provides about 6 hours of imaging because the surgery is so severe that the mouse dies after 6 hours. And we all know that metastasis and the niche formation occurs over a long period of time. So what this fellowship was able to do is bring surgery out into the bedside, and we paired up with the physicist, and this is Dr. Candelas, my mentor, and we were able to create a minimally invasive surgery and create this permanent window for high-resolution imaging called the Whirl. So in short, we intubated the mouse. We made a much smaller incision, exposing all the way down to the lung, small enough just to fit this stainless steel window frame, about 8 millimeters in diameter. And then the key is to completely close the thoracic cavity, reseal it in order to extubate the mouse so that the mouse can wake up and breathe independently, and the lung is completely inflated. So here's just a quick video of this permanent window and how the mouse behaves with it in place. And you can see after just a little bit of time of working with these guys how fond we can become of them. So this window has been validated, and now it's being used widely now in our lab. The one other tool that we paired up with it in order to study this in a temporal fashion is microcartography. And as you know, the lung is a very uniform, large field, so we use microcartography. We use these fiducial marks that we place on the ring before implanting, along with this coordinate transformation system to allow us to get back to the same position post-operative day 1 through 14. And we've validated this in both mice with tumor-bearing lungs and mice without any tumor, and we're always able to get within a field of view every time. So let's see, what can we see? This is the arrival of tumor cells into the capillaries of the lung. And it's interesting to study this process in vivo and to actually see how it occurs in the living, breathing mouse. You could see how the tumor cells interact with these tumor-associated macrophages and how they behave. Next, this is the first ever caught on tape extravasation of a tumor cell. So here it's a 3D reconstruction side by side, just so you could see the outline of the alveolus. And you could see here the tumor cell poking through in between the endothelial cells, all the time interacting with this macrophage and coming out into the alveoli. And that's basically where it sets up shop and where a micrometastasis grows. So when we started, and when I started my time out in the lab, we knew what TMEM does. We knew that it's an area of vascular permeability and the doorway to hematogenious spread. We wanted to know whether this mechanism acts the same way. So once you remove the breast tumor or the primary tumor, can this set up in other places and contribute to redissemination? And finally, in conclusion, it does. It behaves the same way. All it needs is a tumor cell, the specific macrophage, and an endothelial cell. And here in this video, you can see we've colored, oops, let's go back. We've colored, sorry, can you just play the last video? Just put the cursor over it and play it. So you can see how this burst actually occurs. We've labeled the extravascular dextran in magenta, so you could see actually TMEM is active at the secondary site. Thank you very much for your time and attention.